So let us start our discussion today on sorry, fractional slot winding. So you may be surprised to know that how slot can be fractional. So what is the issue here? Let us assume an armature structure of a three-phase machine which is having slot per pole is 9. So it is not a very weird situation. We can have it like you can have 18 slots machine with uh, on 18 slots 2 pole. Now let me draw the structure quickly here. Like I'm trying to draw it. I do not know how much I can draw. So this is your stator. So what you are having here, you are having 18 conductors here. So if this is 1, so 18 means 360 by 18, adjacent angle is 20 degree. So in that next it is 1, 2, let me draw it. So here I have tried my best to draw a diagram. Now see what does the problem lies. Like let us consider a cylindrical rotor structure. So what you will have here. Now even if this rotor is cylindrical, but obviously the pole arc. So what is the pole like? If you want to consider that pole arc should be how much? It should be like we can draw it that it should be well. So in one side it is 6 to 14 and in another side it is this, right? Now see, obviously this span is 180 degree, but pole arc cannot be 180 degree. So let us use red color to indicate this pole. Let us consider this is your 120 degree. Similarly, consider this is another half. So this side north, this side south. Like it is having 60% of pole pitch. Pole arc. What is pole arc? Pole arc is this red shaded region that is 60% of your pole pitch. So pole arc by pole pitch is 0.6. Now think about this, that where does the problem lies. Like if you try to figure out, then what is the amount of uh, like what is the means here we are having 9 slots, 2 pole. So if you now multiply these 9 slots with this point 0.6, then you will get 5.4. Now obviously this 5.4 slots doesn't make sense. What you will having here, like at one time your pole will means have 5 conductors, and in another instant it will have 6 conductors. So that it will continuously means oscillate between slots under each pole face will alternatively be 5 and 6. So what will happen? What will happen? The resultant of your, or sorry, a reluctance of your circuit may vary, as well as the whole thing will become quite like quite this problematic. Now let us do what we can do, like in order to solve this problem we can think about having like this will like, well, 1 5 another 6, 1 5 another 6, it is very problematic. So I hope you understand my point, that and also this problem will be much more predominant if instead of this circular one, if you consider it will having means this kind of projected pole shape or salient pole machine. So in case of salient pole machine, you can also understand that how it is very difficult. Like one, the pole is spanning 5 slots. In the next instant, it is covering 6 slots. So that is very difficult, and that will produce some, the reluctance of the entire circuit will pulsate, and thereby it will produce a high frequency harmonic in the induced voltage, and that high frequency harmonics in the induced voltage may interact with your nearby telephone lines or any do remember one thing, that voltage harmonics has a tendency to interact with your nearby communication lines. They are very disturbing, and what you can get it here, like it's very easy to understand, not a rocket science here. So how to solve this problem? Our agenda is that how to solve this problem. So this problem can be solved like we can have, instead of having like one way out, what we can have, like we can have a number of slots that is multiple of the number of poles also. Like instead of 9 we can means 18 slots, we can have what, we can have like just a minute, somebody has texted me. So what we can do is that instead of selecting a number of slots that is integral multiple of our, like our poles, like here we are having 18 2. What would happen if we select 15 number of slots? 1 5. I'm talking about 1 5. Here, while selecting slots, we must remember that we cannot do any like any alteration or any politics with the phase winding. Phase number of slots you allocate for phase must be equal for development of a balanced winding. So the number of slots are bound to, like slots, number of slots should be an integral multiple of 3 for 3 phase, and there is no need to have integral this one. So how this will do it, we'll discuss it. That uh, let us take one example so that will give you a better understanding. Like here, a single layer winding. I'm taking this example from the book of my favorite book, A.S. Langstop, where they have discussed that it will tax me a lot, obviously, because they are talking about a machine with 42 slots, 10 poles, a real machine, not a toy one. Like, so here one thing you have to, and obviously 3 phase, so we have to figure out how to, and also single layer. Fortunately it is single layer. Had it been double layer, or means we will develop double layer, no issue, but for the time being it's single layer. And obviously we will look for a full pitch case. One question that can also be asked in this regard, that can we develop a short pitch or means corded winding that I have discussed in my last video with a single layer winding? Think about it. Anyway, so what we can have here is that, like, if you find out that slot per pole per pitch, what number you will get? That is 42 by 3 into 10, so 7 by 5. Clearly it is a means not that good way to do it, like slot per pole per phase. However, that there is a common factor, like let me find out, we have already find it out, like slot per phase. So slot per phase is 14, and all the phase should produce what? All the phase winding should produce, like, you are having 3 phase winding, each of them, like A will get 14, B will get 14, and C will get 14, right? Now try to understand one thing, that for a 10 pole machine, all of them are responsible for production of 10 pole. It is not that if 3 poles, 3 phases produce 10 poles, the total number will become 3 plus, means 3 into 10, 30. It's not like that, because your winding current are sinusoidal time varying. So when one will reach at its maximum value, other people, or means other phase currents or induced voltage, they are not at their maximum value. So obviously whatever the resultant you will get, it's very simple, that individual of them should produce like all these 3 phases, all the phases are responsible for production of 14 poles, or in case of it's you are means operating in generating mode, all of them should be capable of means interacting with 10 poles. Now obviously A cannot get all the 42 conductors, A can get only 14 conductors of its share. And what is the common factor between 14 and 10? That 14 and 10, you can see that 14 slots per phase, and pole produced, number of poles number of poles to be produced by this 14 is how much? 10. So what is the common factor? We'll get a common factor of 2. So if you consider that 2, then it will give you a very important thing. Like we can say that we can say that 7 consecutive slots your 7 consecutive slots, not 7 consecutive slots, like 7 consecutive, sorry, 5 consecutive poles and 21 slots. Now here one thing you can see that we can define, it's like the characteristics ratio, that is 7 is to 5. How to use this 7 is to 5 we'll discuss, because uh, like individual phase will get 7 slot for production of 5 poles. Why we are dividing it in half? Because once we realize it for 5 poles, then we'll keep on repeating it and we'll get the total for 42 number of slots. Like first we'll do our experiments with 21 slots, and that 21 slots should produce 5 poles. Now obvious question that should come in your mind, that poles cannot be an odd number, they always appear in pair. Yes, we admit that, but for that we'll have just opposite of our existing arrangement, and they will produce the, means uh, you can say that complement of this first one, right? So this is the thing. Now see that beautiful thing here, like we can find out something which is called that I would like to show you something, like if S is the total number of slot, then Sk is, here in our case it's 2, then Pk is P by K. So in our case K is 2, S you know, S is 42 and P is 10. So how to do it? Instead of means just like describing it verbally, let us draw the slots and let us try to do it. So while instead of drawing the slots, let me draw that circles that will indicate the many shapes are there. Let us pick up this one. We need 21 of them. One. Okay. Limit. The problem is that they arrive in black color, not in white. So let me quickly draw 21 circles and you also draw it. 1, 2, 3. They are actually the slots. 4. We need more space, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So we have 21 number of slots. Now we will see how we can fill them up. Well, so here, see what is the issue. Like if you calculate the angle between adjacent slot in electrical degree, what you will find, it is like your poles are how much? Poles are 10 poles into 360 by 2 into your total number of slot. So this is like, you should get it something like 42 by 67 degree. So 42 by 67 degree. Now how to use this 7575 whatever we are getting in this way. So let us start placing. So let us consider this first coil is at the center of one of our north pole. Now, what is this angle? This angle is 42 by 67 degree. Fine. If this is 42 by 67 degree, then if we consider the narrow spread configuration, then obviously we should put the winding of Fs here. Like this should occupied by Fs, this should occupied by Fs. Now, after that, what we should do is like, we have to determine the position of like one thing we can do, like instead of doing it in conventional 60-degree spread where it is an integral slot, it is easy for us to figure out. But here we will do something else. What we will do, we will not do that only narrow spread, but we will consider that if this is like the range of, means since we are considering the half, we will consider if this falls under 60 degree, then it is within same spread, and then the next one will be means we did allocate this for A, like in the first, here it is A, here it is A. Now generally what we do, we place it 120 degree apart from A, but here what we will do, we will do it like, since we are taking just the half of the winding, not the whole one, we will consider that we have to For the first 7 conductors we will take, we have already fixed up the means fate of 2 conductors. Another means 5 conductors fate has to be determined, and in this process what is required, like this is 60 degree, then we'll draw another 60 degree. This is 160, another 60, and then here another 60 we have to draw. So in the next slot, when we will try to fill up the next slot, instead of keeping it vacant for C phase, we will place the winding of B phase here, like so. This is B. Now for the next 2 slots, what should we do? Why it is B? Because adjacent this one is this, so if you obtain twice of this, it will give you something divided by 27, sorry, not 27, it is 57, 85 by 57. Now it is clear that when you will multiply it with 3, you will get what? You will get 128 47. So since it is 12847, so that means you have already covered up 60, then 120, then you are here, it should be 120 to 180. So therefore here you should fill this up with the winding of C phase. Then like I'm talking about adjacent conductors, like from this red to this it is 42, from this to this it is 85 degree 57 minute, then from this to this it is 128.47, then again let me do it like 120 like 4. This is 1 2 3 4. Now when you are at 5, then what is the total angle difference between A and this? This is 128.42 degree 67 into 5 minus 1. So how much you will get? They have not written it anywhere. Just let me calculate. So here it is 42 into 4 plus 3, like it is 171 degree, this much degree will get. So I am not good at calculation, so I am getting this value. This is still less than 180 degree, so this one should again be filled up with C phase winding, right? So now here when we have reached here 180 degree, then obviously we are free to consider that if this is our N pole, we must have one S pole center line here, that is at 180 degree. Now see, what is this angle? This angle is how much? So similarly you can find it out. This is slot number 6. So 6 minus 1. So let us calculate 42 into 5, that is 210, and like it is 214. Now it is like greater than means 180 degree. Next, so basic idea, let me write 0 to 60 degree A, then 60 to 120 B, then 120 to 180 C. We are not concerned about how many slots will fall in this span. Whatever be the number of slots will fall in this span, we'll keep on filling them with this phase. Then 180 to 240 A, 240 to 300 B, 300 to 360 C. That is our whole game plan. So now it is 214 to 7, that is in this range. So let us fill it up with A. Then for 7, this is slot number 7. What is the picture? It is 42 into 6, that is 252 plus like 257, 17 degree. So it is in this range. So here it is B. Now what about that when we'll change it to slot 8? Slot 8 is 42 into 7, 294 plus here it is exactly 300 degree. However, as it is like 300 degree, here we have to make one compromise, like uh, for 300 degree, instead of taking B, as you can see that this is quite overlapping, will means from idea of corded winding, we'll try to just means we should not exceed call span to 180 degree. It should be less than or something equal to, means there is no harm if you slightly take less span rather than 180 degree pole pitch. So 300 to 360 degree, let us give it to, means 8 is, as 8 coil was giving or demanding 300 degree. Let me check once again. It is pretty interesting for uh, this 8. Yeah, I didn't make any mistake. It is 300, but we will give it to instead of B, we will give it to C. So this one C, and obviously this is again 342. So 9 slot, 9 slot I can do without any calculation. That is 3, 4, 2, 6, 7. So this should also be like filled up with C. Now, once again, when you reach this total 360 degree span, obviously you can expect one like in conduct, means in pole should be here. So here one in pole should be here. Now see, here you can keep it on, and I hope you have understood the procedure how to get one after another. So here you will get it like the same thing you can repeat here, like you can write it this one to be 10 minus 1. Okay, let me do it, there is no hurry. uh, like this is slot number 10, so it is for 10 slot. uh, 10 slot what we are getting, it is 385.71 degree. So 385.71 means next pan, this is 10 slot. 360 to 420 will again be occupied by A. So this will give to A. Then what is the next one? Next one is it's 4 to 8. So obviously as it is 4 to 8, so 420 to like 480 will be B. So 4 to 8 means we have to give it to B. We give it to B, then it is 471.24, like this one was giving, this one was giving 4 to 8 point something, and when this is for 11 slot, when we are at 12, then 12 is will be something like 471.84. so marginally this also belongs to our B phase, so B occupy them. Now I hope you are not getting confused. This is for our B phase conductor. This is for our A phase conductor, and this color is for our C phase conductor. We are just taking the front view, right? Now the next angle will be how much? Obviously it will go to C. So 13 minus 1, it is 514.28. So for 480 to 540 is again C's domain. So 514, that means it is occupied by C, that is 13 number slot. C takes 13 number slot. Then again it is the next slot, that is 14. We are getting 557.24. So this belongs like once it exceeds 540, so it is again you exceed 540, it is again 5400 to 60 is the range for your A. So what about A? It is this one. A. Fine. Now, then what is the case? Now 5400 to 60, it is okay. Once you reach 5400, it is time to draw your another pole. So where we got 540, it is just before our slot number 14. So here it is like exactly 6, yeah, 14. Okay, now what about our other slot, like your your this one? So 14 is occupied by A. Now so let us consider or decide the fate of 15 slot. That is, so 15 is again the same thing happens. So what we got here for B. So again we cannot give it to A. This will be taken away from A by phase B. So here, because if you do this, then you will get, this will give you 600. Well, so this is slot number 15. What about slot number 16? Slot number 16 will be your, like here, so this 642.85, that means they are still under the band of 660. So again, 600 to 642 should be for B. So B took these two. Now what about 17? 17 is, it is like 685.72. So what about this 685.72? That is in the range of 660 to 720. So 660 to 720 means it will be occupied by C phase winding. So let it occupied by C. Then what about the next one? So next one is again we are having this okay, okay, fine. 5 pole means yeah, okay. So 660 to 720 means what? 660 to 720, and it exceeds that. So this will again belong to A. Like once you accept this 660 to 720, 720 to 760 is for A. So when you do this you will get it 728.58. So that is for phase A. Now again the next one will be occupied by, it is in 771, so next one will be taken by B, because B is in the range of 760 to 820, so it is B. Now sorry, 780 to 22, I have made a mistake, sorry. It is A, because why A? Because for slot 18, 19 it is 771.44 and it should be 720 to 780, to 60-degree span we need. So these two are A. Then obviously the next one will belong to your B, and then like next one will be how much? Next one is like when you are here, you will get it 814.26. So 814.26. That means it is in the range 780 to 840. So it is B. And obviously the next one, that is this should be 840 to 900 should be in C, should be given to C. Now should be given to C. Now let us check quickly that whether these slots means, I just do one thing, very simple thing, that if it is first 60 A, second 60 B, third 60 C, I keep on repeating for all this, and I didn't consider also that whether which slot will be occupied by which one. So by doing so, what we are getting here, it's like, see how many slots we have given to A. A is like here 2, 1, 1, 1, 2. So A total 7 slots. Then let us consider B. B is there at 3, 7 means 2, then another 2, 4, then another 2, 6, another. So B is also 7. And what about C? Obviously remaining should be match, like 2, 2, 8, then sorry 2, 2, 4, then 1, 1, 1. So C is 7. See the beauty that we just follow a definite pattern, and how we are getting and means balanced allocation. Like we were not considered that we have to give each of them equal slots, but eventually we have given it to them. Now what is this? Oh God. So now it is quite clear to us, just like it's very simple thing. Just let me clear this board first. Yeah. So here, if we write it, then we'll get a very interesting thing. Like you can write it like uh, for slots, it is A, B, C, C, A, B, C, C, 1, 2, 3, 4, 5, 6, 7, okay, 7. Then 8, 9, 10, 11, 12, 13, 14. What are they? In 10 we have A, then B, B, then you are having this like what you have here at 13. 13 is for C and 14 is with A. Then 15, 16, 17, 18, 19, 20, 21. So 15, 16, 17, 18, 19, 20, 21. So what you are having at 15, see at 15, 16, BB, then it is 17, it is C, then it is A, then 1 means B, C. So now let us group it. How to group them? Let me try. Like first group, then the second group, and then the third group. Each of group this contains your conductors, and see more beautiful things means that is more not beautiful, rather let us say it is very enticing. Note that we can find out a definite pattern here. It is 2 1 2, like this is 2 coil belongs to same phase, no sorry not coil, 2 conductors belongs to same phase, then 1 coil that is different, then another 2 coil of next phase, then again 1 1, and we will be observing that this pattern, if you add these numbers, it will be like 2 plus 1 plus 2 plus 1 plus 1, definitely they will give you 7, and they should. But if you see, interestingly, very interestingly, you will see that here it is again 2, then 1, then 2, then 1, then 1. For here also, first 2B, so 2, then 1C, so 1, then 2 consecutive A, so 2, then 1, 1. So how to memorize and why I have selected these colors. If you have forgotten the color selection, let me show you. These are the selection. So see, we can for this we can claim that here we are starting with like you can say this is for A group. So this is related to A phase. So the first 2 conductors you will give to A, then the next one should be given to B, then the next 2 should be given to C, then again A, again B. The second one, see the beauty that although we didn't have it at the first place, but right now we are getting that our common configuration what we usually have, like for basic 1, A dash, C dash, C, B dash. So in between A and B, one C is there. And see here what we are getting. This group is for that C. So you can say that this is for C, and this group, first two conductors will start with C, next one will be what? You should make a complete turn, like once it is over A, B, C, then again A will come. So 1 will occupied by A, then 2 will be given to B, then again 1 should be given to C, and the next one should be given to A. Now the last one, that is also the same thing is happening, like this one, it is first 2 is occupied by your B, and this is B group coil, first 2 B, next one C, next 2 should be occupied by, after C what phase should come, again A, so next 2 should occupied by A, this 2 is basically 2A, then 1B, 1C. See what is that, means how beautiful and how enticing these things are, that you have got an arrangement number, so you keep on repeating this for your next, like this is for 5, and for next 5 you just keep on repeating this, and you will have a complete slot distribution for 42 number of slots. And it is not for 42, even if we have something like, we can do the same thing. Here we have shown the last pole, I just didn't draw. It should be like, if it is 30, then approximately where it should be, like where 720 degree was apart. Just a minute, I am drawing the last one. I forgot to draw it in the first place. So it should be here. Another north pole should be here, and then actually this one. So north, south, south, north, and again you will have another south, typically after this, like another south should be, this is how much? So 720 plus 180, 900. So another south will be there. That should be at an angle, means at 900. So we'll draw it after a certain time. So now you can see that on an average you are having that 4 or 5 number of means are under that one. So we got this distribution, and it is very easy to understand that how for this fractional slot we can use the index number, and this can be done. This same distribution will help us to design a 84 slot 20 pole machine, or whatever be the case, we can draw it, right? So here the position of north poles and south poles are also given. If you have that book, you can find it in that is Langstop. Now we will do it for two layer and fractional slot. We can do this, but this our lecture has means you will do it in your machine winding design class also, because there will be a complete sessional paper, and goal of this course is not to devote too much time on machine design, rather to discuss another special issues of or not special issues, rather very generalized issues of rotating machines, right? Instead of dwelling with this winding and different winding structures, what we will do here, that gradually we'll try to investigate that how having a distributed winding can be helpful for us. But before I start, I would like to remind you one more thing, that we should not forget, it is our that EMF, or rather let me write clearly, the time variation of the EMF induced across a coil exactly mimics the space angle variation of the flux density inside machine housing. In my last lecture, I have also shown that this machine flux density variation with respect to space angle is quite often not sinusoidal in nature. Rather, they are non-sinusoidal waveform. And most of the times they have, or they preserve, half wave symmetry, like successive half loop wave loops are symmetrical to each other, right? They preserve half wave symmetry. So with this, let us proceed, and we'll see that how, instead of having a concentrated full pitch winding, how having a distributed winding can be beneficial for us. So let me write that, like for radial component of field intensity in the air gap, if that is represented by a sinusoidal curve like this, Just a minute. So here you can see that this is our waveform for flux density, and for this flux density waveform, if we can have it like here, this one, then we can write that the EMF space variation of EMF can be written like E is equal to 2 pi f n phi sine omega t. So where, let me write it again, f is frequency in radian per second and phi is flux per pole that is in Weber, and then you are having n, capital N, that is the number of turns, right? Now what we can write is that for sinusoidal distribution, your EMF RMS value capital E is root 2 pi f n phi. So that gives us the very popular formula 4.44 f n phi. Now, like this is true when the coils are means you are having a concentrated coil, and the, like, what is meant by a concentrated coil, how we are getting this, like if you understand that when you are having the two coils like this, you connect them in this way, then again you are having concentrated coil. Okay, let me use two different colors so that will help you to understand. Like red color indicate the upper layer coil, then and blue color indicate lower layer coil. So here now this blue will get connected with this, and this portion generally we call this dummy end as the overhang of the coil. So sorry, not this, yeah, yeah, this red you should connect it with this blue, the lower layer, and then this blue should again get connected with this blue, the upper layer. Then this blue should connected with this red, and you are having these two conductor from the red end, right? Now here the question is that it's very easy to understand that if we, it is like having a concentrated coil, like maintaining exactly pi angle difference between them. So if you if you can understand that if means in a single turn coil, if across a single turn coil you can get an RMS voltage 2 volt. Then for an n-turn concentrated coil, you will get how much? 2 into n. However, I would like to go back to again to that picture from where this discussion started. Like here you can see the your coil ordinate. This is one side of the coil. Like let me use different color. Say this is one half of the coil. So if this is here, then the other half, in case of a concentrated coil, where you can find out the other half, obviously the other half will be somewhere here. Like this is the flux variation, so the other half will exactly be 180-degree opposite of that this one. So if this is at 120 degree, we will find it at 300 degree. This is we are doing this for rotating armature, but the case remains same. It is all about the relative motion, not about the absolute motion, whether your armature is rotating or your field is rotating. Now, if you want multi-turn, then what you will do? You will place one more conductor here, right? And here will be another one conductor. So, depending on the number of conductors, you keep on placing conductors on the same slot. So, the two side of your intern coil, all of them are full pitch, means concentrated coil, and having means like they have the means voltage gap. It is means they are exactly 180-degree electrically phase apart, right? Now if you can figure out that the total coil across total voltage across that intern coil is like uh, or not intern, we can also write it is okay, intern coil is E, then for in it is En. Here there is, if we now instead of placing all the turns in a single if we do it like this, if we start placing conductors distributedly, then what you will have? You will have one conductor here, another conductor maybe here, another conductor maybe here. However, the coil will remain full pitch. Like for one end, you will have for the part that is at 120 degree, you will have the other end that is placed at 300 degree. For this one, say this is at 100 degree, so you will find it at 280 degree, like this. So obviously this is difficult to draw because let me try. This is the 280 degree slot, then you will have 300 degree slot, right? And similarly for this you will have exactly 180 degree plus. So what we can say that that if we take an arrangement like the arrangement is of n turns concentrated winding spread out, and now instead of means placing all the n turns in a single means inside a single slot, what we are doing, we are having n turns coil placed at q slots per pole. So it is the q slots per pole, and in addition, let us assume that the adjacent slot angle is gamma. So we can draw it pictorially, means we can have a pictorial representation. This is the case of our distributed winding. Now see that like if you have E so distributed winding means you have one end here, the other end must be 180-degree apart, but for means one side of the coil, instead of you place one side of the coil in a single slot, you may take 4, 3, 5, any number of slots, so it is getting distributed. So if you have trouble in visualizing, let me show you something here. Where? See, this was a case of double layer winding. Even if we consider a single layer winding, the first one which I shown you, that was you are getting whenever your number of slots per pole per phase becoming greater than 1, your winding will eventually become a distributed winding. The paper model which I shown you in the last video using some paper and some loose bare means loose conductors, loose conducting wires with insulated coating. So that one is a case where you are having something like concentrated winding. Why? Because in that case, although you are having 12 slots, but if you find out the number of slots per pole per phase was 1. However, here when we reduce the number of pole, you can see that it is 2 slots per pole. And for this case, what is the slot angle? That is 30-degree. So whenever it is easy to understand that whenever this, if you consider this one, this FS coil, see this is a full pitch coil having total 180-degree pitch. It will reach its maximum value. After 30-degree, the next one will reach its means peak value, and obviously like if you place both of them in the first slot, then you could write if one coil is getting total 2 volt across its two arms, induced 2 volt across its two arms, then the another coil will also have 2 volt, because and there will be no phase shift. The means arrangement I am talking about, instead of having it here, let me draw it using white color, that you are having the other conductor, and it is like this. Suppose these conductors are not present, you are having this. So what you will have a case of concentrated winding, and you will have 2 volt plus 2 volt if you write means connect it in a correct polarity. So total 4 volt induced across this conductor. However, when you consider this, then which was the case, then obviously it is not same as the previous. So what you will have when you consider it is there is something, then this one is 30 degree, and in terms of vector addition you can find it out like one is say at E, and the another one is how much, you can write it like well, or means you can write it even uh, like plus 30 degree also, the way whatever you want to represent. Then what you will get it like 1 plus cos 30 degree like plus j sine 30 degree. So actually when you will try to find out the value, the value will be something like, instead of twice e, it will be 1 plus root 3 by 2, right? So all these things are there. Now let me, instead of means dealing with a particular one, let us have this. So now adjacent slot angle in electrical is gamma, means in that case it was 30 degree and now it is gamma. Now let us have q number of slots here. So if N turn coil, total EMF induced across this N turn, if we assume that total EMF across N turn is E dash, then what about individual coil? Like we can go by unitary method, we can see that individual coil or rather individual slot combination will have E dash by Q amount of your means like uh, your like let me just clear it once again. So or we can write like, if E is the EMF, instead of writing that let me write it clearly, that if E is the EMF, that you can get across the total N turns then EMF across a single turn will be how much? E by N, right? Now N turns are uh, means placed at Q slots. So if N turns are placed at Q slot, so total means N by Q number of turns are available, means are like available at a single slot. Now if this is the case, then we can write that E by Q into like E by N into Q is the like, yeah, E by N into N by Q. N by Q is the number of turns and E by N is the EMF across individual turn. E by N is the EMF across individual turn and N by Q is the number of turn per slot. So we are getting E by Q is the amount of EMF across a slot. Although this is kind of virtual, not physically realizable all the time. So E that Q. Now this we can write like E dash is equal to E by Q. That is proportional EMF now what we can write like in this way, if this is our slots, like we do not know how the slots are there, say we only know there is gamma and this number of slots are q, right? This number of slots q and we are having full pitch coil. So this side is also Q and full pitch coil means from the first conductor of the one group will go to again 180 degree the other group. So it will be like the total EMF E1 is equal to E dash. What about the next? Sorry. The next EMF, if this is E dash, we can write it like 1. Now if this side you consider lead, then it is e to the power, for the second slot it is e to the power j gamma. Then for the third slot it is e to the power j 2 gamma. And likewise you will get it. It will be in that Fine. So this is the bracketed term forms a geometric series, and you can write it like where what is A is the first term. Now what is R? R is the ratio is equal to a J gamma, and then N is equal to what? So basically what you will get it like E1 is equal to E dash e to the power j q gamma minus 1 by e to the power j gamma minus 1. So e to the dash sin q gamma divided by so in numerator denominator only term difference is q, and obvious it is because q is the number of slots. So if you further simplify it to find out the real value, you will get E is equal to, you can easily find it out like doing root under and you will eventually find it like you will have and that term, that is E by this whole thing, is known as breadth factor or distribution factor. So this factor, this sine q gamma by 2 by q sine gamma by 2, where this q is the number of slots and gamma is the adjacent slot angle. It is interesting to note that this factor is known as breadth factor. So, or sometimes we call it distribution factor. Now, just try to understand one thing, that how this distribution factor or breadth factor can be of any use. See, when as I have mentioned in my last lecture, that like two things are very important. Time variation of your EMF in conductor will exactly, for concentrated conductor, will exactly same as the space variation of your flux density waveform. And flux density waveform, quite often they are non-sinusoidal, half wave symmetrical. In addition, they satisfy the Dirichlet condition, so we can represent them in form of our means Fourier series expansion. And if we expand them in Fourier series, then what we will be getting things like uh, higher order harmonics. You will get like there will be something like uh, if your it is sine omega t, then you will get b1m sine omega t plus b3m sine 3 omega t plus b5m. Generally, as it is half wave symmetric, so only odd harmonics you can expect. This is the general b of theta. So or here actually not sine. This is also sine theta. Sorry, sine 3 theta, sine 5 theta. Now see what is there, like what is 3 theta and what is 5 theta. These are the this flux equation. It is the in terms of space harmonics. So in terms of space harmonics, so when you try to talk about them, like sine, I think I have already explained it. Now for the timing, let us quickly recall the concept. For time harmonic, suppose this is your t. If this is sine t, sine 3t is expected to execute 3 complete oscillation within this period. So this is our sine 3t, right? Now in this sine 3t, you can see that it completes similarly. This is our sine t and sine 3t, and in this direction we are having our say a1 sine t, a3 sine 3t in this direction t. Similarly for flux waveform, this direction theta. So when your main flux, that is b1 sine theta, it will execute 1, then b3 sine 3 theta will execute 3 complete waveform, right? So it's okay, we understood that. Now this is b theta. Here in this direction it is theta. So obviously when you will apply here for third harmonic third harmonic space variation will give rise of third harmonic EMF. But see what happened due to your breadth factor, that for third harmonic, instead of considering this as gamma, for third harmonic it will become 3 times of this, right? So 3 times of this will cause a considerable means attenuation to third harmonic in comparison with your first harmonic. So if you want to understand this, let us take one example, like say say number of slot q is equal to say 6, and what about gamma? Gamma is what? Do remember this formula, 180 by 3 into 6. So gamma is equal to 10 degree. Why? Because generally one coil span, here you can see that this one coil span is like number of slots under one pole, then that is uh, here you can see that what is your q? Q is 2. So what formula I was trying to write? The slot adjacent angle gamma is equal to 180 by q into 3. So here your q is 2, so you can find it out, that is 30 degree, which we already studied. It is obvious that if you increase gamma, your that A will decrease. Now see what is happening here. Gamma 10 degree. So let us calculate the factor, that is sine, the denominator it is 30 degree by 6 into sine 5 degree. So what you will get here is interesting. Like sine 30 divided by 6 divided by sine 5. So it will give you 0.9561. Right. So 0.9561. Now what happened when you will have third harmonics? Let us see what is the case for third harmonics. So the same number of slots when you are considering for third harmonics, it is what is the angle covered for third harmonics? See, when your first or fundamental harmonic can traverse only 90 or 180 degree, within this span, the third harmonic has already traversed how much? 540 degree. Try to understand this. 540 degree. That 540 degree. So therefore, for third harmonics, you should get it like sine. Here it is how much? For third harmonics, it is 90 degree by 6 into your sine 15 degree. Let's see what you are getting. it will give you. So this is a considerable reduction offered to, means if you consider these two factor, this one is for fundamental distribution factor, and this is for third harmonic distribution. Similarly, we can find out fifth harmonic. We do not waste our time with third harmonic because third harmonic can be cancelled out using some like waveform. No, not waveform, like winding connection. We can cancel out that third harmonic. What about fifth harmonic? Fifth harmonic, it will be how much? It will be sine 150 degree, and here it will be sine 25 degree. So let us see what we are getting. Sine 150 degree divided by 6 divided by sine 25 degree. So for fifth harmonic, see the beauty, it is giving me 0.197 for fifth. So more higher order harmonics you take, you will see that this distribution factor is so designed, it is more harsh and more means rough on the higher order harmonics, and will give you a very high attenuation for the means as you move on towards your higher order harmonics, it will give you more attenuation. So that is very interesting things. Now another interesting thing what we can have here is that if we have a very large number of slots, like interslots angles are very small, very tiny, and this is very large, like what we can say that this special case like Q approaches to, and therefore it implies gamma, the interslot angle approaches to 0. So what you will have here, like we can write the total phase spread of the belt is how much? Total phase spread of the belt is and what about this Q minus 1 gamma? You can see that this Q minus 1 gamma always remains same. So it will be like saying and what about the other end? Like we have to figure out the total formula. The total formula, how to find it out? Like if we expand it, we'll have two terms. Like one will be, it all started from there, like in the previous case we got this geometric series, but before we got this geometric series it was like E J Q gamma. So E j q gamma. The denominator part is it was started E j q gamma minus 1 by E j gamma, sorry, E j q gamma minus 1, and this one is E j gamma minus 1. So you can figure out or smell the means trouble here, because if you make gamma tends to 0, the denominator is going to be 0, because gamma 0 means e to the power 0, so that is 1, 1 minus 1 0, and in the numerator also it is a very complicated situation for you. Now we will take help of Euler. Whenever we engineers find ourselves in trouble, Euler comes in help. Like you can write e to the power j gamma, jq gamma into means we can separate the real and imaginary part. The real part is 1 plus cos q gamma plus cos 2q gamma plus cos your cos just a minute, yeah, here it's cos j gamma plus cos 2 gamma, like, and then till plus cos q minus 1 gamma, and the imaginary part is what? It is like started with I'm making so many mistakes here. As it is imaginary, I am not writing j with it. This is not careless mistake. This is intentionally I am omitting j writing here. So basically we are having two series. One is cosine series, another one is sine series. Like the cosine series, if we multiply with, you can see that this cosine series is going to be multiplied by one more term, that is e by q. So you are having, and also you can understand that if we increase q to a very large number, you will have plenty of numbers here. And one more thing that is understandable, that if you make q very high, you are basically means trying to means reducing the value of this gamma, and therefore this cos gamma, cos 2 gamma, cos all these will, at least the first few terms, will always give you value very close to 1. So if you do it, you will get something like e by q 1 plus cos gamma plus cos 2 gamma plus cos gamma minus 1 gamma. So if you do it, then what you will get, that this whole thing can be represented as, like, all it started from the same equation. Only thing is that here cos and means this q is very very large. So you will get it like, it will be your u1 cos q minus 1 by 2 gamma, And for sine, if you do it, the sine will be giving you sine will be, if you just write these terms, sine gamma plus sine 2 gamma, just wait, let me check whether, yeah, it's recording, plus last term sine q minus 1 gamma, you will get it like sine qy by 2 by sine gamma 2 into that same like cos sine q is equal to sine q gamma by 2 divided by sine gamma by 2 into sine q minus 1 by 2 gamma. So these are the case. Now see, from this what we can write, that the limiting value of q sine gamma by 2, we can write it like, when sine theta is very small, we can replace it by that sine x is equal to x. Applying same logic, we can write sine gamma by 2 divided by 1 by q is equal to sine gamma by 2 divided by gamma divided by y plus gamma. How we are getting this y, gamma plus y, from this equation. So it is easy to show you that in his case, it is, if we put limit gamma tends to 0, then it is like sine gamma by 2 by gamma psi plus gamma, and that will result you y by 2, right? So basically you are getting something like the breadth factor will be, when you have a very large number of your q, it will be sine psi by 2 divided by psi by 2. Now, one thing, do not forget that when you consider this psi by 2, this psi is never in degree. If you consider it in degree, then it will be a suicidal atom. This one is always in radian. So, what is general value of psi? Normal case. For narrow spread coil, what is value of psi? If you recall, it is 60. So what could be the value of, means I am telling you 60, that means it is not actually 60, or better we will say it is pi by 3. We have to develop this habit instead of telling 60, 30, otherwise we will make mistake. So what we will get here in radian, like 0.5 divided by is, so we'll be getting something that is 0.318, right? 0.318. Now whatever result we have uh, means received here by doing mathematical manipulation, the same thing I can show you by geometric structure, geometric construction. uh, Let me do it. So your one coil that induced voltage is having an angle, this is E dash. Now the next EMF next in the coil EMF E dash will be like, so this coil axis is this one. Now the next EMF will be, that is exactly making the phasor E dash, making gamma with this line. Then similarly for this we can draw and we'll get another phasor that is making gamma, sorry, gamma with this line, and then another phasor, so that is making gamma with this line. So all these like this. Polygon, all the sides are E dash and all these are means and having an angle gamma. Then here it is now. So how many angle you should traverse by having this gamma? One thing you should not forget, that this Q gamma should always give you how much? This total Q gamma, it should give you that 180 degree, right? So Q gamma should always give you 180 degree. Therefore so now to understand the previous discussion, like here this geo means uh, manipulation. If you find it a bit difficult, let me draw a simple picture for you. You will be surprised to note that this individual voltage phasor, uh, what is the total angle span by the all means, if you find out, if you traverse electrically, uh, if you make a traversal of, then electrical angle traversal should be how much? 360 degree. So all the phasors whatever you are getting, they, like obviously you can argue like if you are not getting, let me go back to that picture of here where we started. Not this one, yeah. So here you can see that, oh, not this one also. So what I'm trying to say, it's very simple thing that once you cover two pole, then each of these slot is how much? Each of these slot consume 60-degree angle spread. So once you reach the end, you are having total 360 degrees. So now it is easy to understand that two means, forget about which phase they belong. Think about what is the phase difference between two uh, conductors induced EMF. That is the slot angle of electrical slot angle, and irrespective of its phase difference, it is always the same, that is gamma. Now from here to here gamma, here to here gamma. In this case, what was the gamma value? Probably it was uh, like it was 30 degree. Yeah, it was 30 degree. So from 1 to 130, then here 30, 30, 30, 30. So what I am trying to say, that if you traverse the total two pole pitch, like here from 1 to 12, what you will get? You will get a simple thing, that by means adding up those gamma, those interslot angle, you have already covered that 360 degree. So now let us give you a simple and easy to understand approach. It is my habit of discussing the difficult thing fast, because if I discuss the simple thing fast, then people will not listen to the difficult one. The difficult one is like a mental drill. It's like a brainstorming. It will means increase your ability to deal with complex system. Now here, so if there are four slots, four adjacent slots, say four adjacent slot we are having, say these angles are gamma. Now obviously we can, from that our preceding discussion, we can easily conceive them as like they are the chord of a circle. So let me show you. This is say one EMF. This is say another one. So how to draw one from another one? Or you may do it in a very simple manner, like we can have it like, let us start with this, considering this as a reference. So this, then the next one should make an angle gamma with this. So let this be gamma. So it will be like, now the another one should make another gamma with this. So it would be like, then the fourth one should also make an angle gamma with this. So we have drawn these phasors, right? Now what more we can do is that to visualize them as they are on the arc of a circle, means they are the chords of a circle, like here. Or let me draw it quickly, like what I'm trying to say, that in this circle we are having, say this is first one, let it be E1 or EA, not EA, let it be let this be our AB, this be BC, this be CD, this be B. So what we can do here is drawing, this is our AB. Now that BC will exactly gamma angle with AB. So this is our BC. Then we can have our CD here, that is also making gamma angle, and then we are having our DE here. Now what is essential thing now what is the essence of drawing this diagram is that you can have a center of this circle for which this induced EMF are serving as a chord, and angle between two individual chord is gamma, like angular orientation of one chord with respect to other is gamma in anti-clockwise direction. So now what we can have, like we can form a triangle with center and the 2 point of this. Just a minute, let me complete the diagram, then I'll show. So we are done with our drawing. Now let us see what is this angle. These angles are also gamma. So why these angles are gamma? If you find yourself, it's quite surprising. See that when you traverse all the slots of within to a two-pole pitch, what say if it is the like say x number of slots belong to two-pole pitch or cover total two-pole pitch area, or sorry, two-pole pitch distance, angular distance, then what is the angular span? That is 360 by x, and that 360 by x is nothing but your gamma. So obviously that induced EMF will like it will, if we draw or if we join the two end of this induced image, it will form a like an inscribed angle will be there with angle gamma. Not inscribed, actually we can say that this chord will sustain an angle gamma, and obviously if you add all these, means if you make a total turn, then you should get what? You should get 360 degree. So this is no way surprising that this much is how much? This one is our what? It is E by Q, right? And these gammas are there. Now let us consider that we are having this radius is r. Obviously r, we can have r means terms of eq, but let it be r without any further complication. Then what we can do is that we can draw a perpendicular on this line. So this angle will be gamma by 2, gamma by 2. This should be a perpendicular bisector on that line drawn from your center. So these two will become like two right angle triangle. Now for this one, this is the base of that, like you can say that if you take this right angle triangle, this section is gamma by 2, this section is r. So what is your total r? This total length E by Q is like 2r sine gamma by 2. E by Q is equal to 2r sine gamma by 2, because individual height is sine gamma by 2. This one is r sine gamma by 2, and we have a similar one here. So E by Q is equal to 2r sine gamma by 2. Now we have to find out the resultant. Resultant one is this one, like this is what? This is our E1, right? So this one is how much? What is that? Means we can see this one as like combination or this form. Here this is our center O, and say this is A B C D E. So the triangle formed by AOE point, we can again break it into similar part, like we can have O. From O we can draw a perpendicular on this line AE and mark it as say, let us take different color otherwise. So let us draw a perpendicular on this. Let it be point capital T. So what about the triangle OAT? The triangle OAT, what is this means angle? Angle AOT. Angle AOT is equal to how much? That is Q, what is the number of slot into gamma by 2. So this is our angle OAT and triangle OAT this side. So just by similar arrangement, what we can write, only change is here is Q. So instead of having R sine gamma, what we will have here R sine Q gamma by 2. So the total length U1 is how much? U1 is R sine 2R sine Q gamma by 2. And what is breadth factor? Breadth factor is the ratio, we denote it KB is equal to E1 by Q, E by Q. So that is, you will have like here it is R sine, or rather 2R sine Q gamma by 2, and in the denominator you are having Q into 2R sine gamma by 2. So basically that leads to same result, sine Q gamma by 2, Q sine gamma by 2. So now what would happen when you will make it very now from this geometry you can easily visualize that what would happen when we will make gamma very small. If you make gamma very small, then what would happen? Making gamma very small will result in what? Will result something like, you will have small chord here, right? And then the resultant will be like this. Now this resultant will be what actually, if you have a center, if you fix a center, then the angle subtended by this one remains constant, it is Q gamma. However, for the small triangle, they will just like uh, they will uh, become very small, angle subtended by individual chord, because you are making the chord length very small. So if you keep on decreasing the chord length, then obviously the angle subtended by the corresponding chord at your center will also decrease, and then therefore this one will make thing you will know that whenever sine x is approximately equal to x for very small value of x, so similarly all those, instead of in the denominator, instead of having r uh, like sine gamma by 2, you will have here this sine gamma by 2 can be approximated as q gamma by 2. That's it. But remember once again, as I have mentioned, that you should not forget that, uh, especially when you are taking this, means this is a case of very large queue or very large number of slot within a phase spread. Do not forget to consider angle in radian. If you do not consider angle in radian, the total calculation will give you a very erroneous result. So be cautious. Now I will like to show you some calculation, so that will make your understanding further uh, means clearer on this particular topic. Like we will have slots per pole. Let me create a our pole per phase. The slots per pole per phase is Q. Now that for 2, like in this direction we are having this Q. If this is 2 and in this direction we will have phase. So if it is phase, it is two phase machine, then this would be how much we have to calculate. Now, why I am showing you this? Because this is very important for your gate or other competitive exam. You must understand that slot per pole per phase, when it is 2 and the machine number is 2, then what about it? Like how can we do calculation for a two phase machine? So how many phases will be there? 2. Now we can write it like, just a minute, let me calculate. Then I so well I have calculated, like for two pole two phase. What is the scenario? Do remember that for unlike your three phase machine, two phase can only have one phase spread. That is your Q gamma is always 90 degree. So what is the case for this? Like sine 90 degree by 2, here Q is 2, then it is like 2 into sine 45 degree by 2. So if you calculate, it will give you 0.924. So here it is 0.924. Now if you make it 3, what change will take place? Here just this will become sine 30 degree by 2, and here this will become 3. So let us see what changes it will give you. I am doing so many calculations just to show you how things matters. You will get here, this calculation will give you this whole set of calculation will give you 0.910. Now if you want some higher value of slot like 8 or 6, so what you will get, let me show you it for 8 slots, then I will not show any more. Like it will be 8 and then here it will be, so how much you should get it here. The numerator will remain same, and that is true for all the cases, whether you are increasing the slots to any number, the numerator of this breadth factor expression always remains same, and the denominator, it is like it will give us 0.902. So I hope this calculation is clear to you. Now we'll consider some narrow spread and wide spread case. For narrow spread, three-phase machine, it is Q gamma is equal to 60 degree or pi by 3. I would like to, means although I have a bad habit of telling things in degree because they are easy to utter or means discuss verbally, but I would like to you to develop a habit of means inculcating a habit of always considering radian, because that is the safer choice. So now you can see that if it is like you are having say slot per pole per phase q is equal to 2, then what you will get, I have shown. Let us do it for q is equal to 6. So for q is equal to 6, q could be anything, q could be or 5 also. There is no harm of q being 5. So what we will get it like sine, as I said, the numerator will always remain same, and for wide narrow spread coil, the numerator is always sine 30 degree. Now, what about the denominator? Denominator will be 5 into sine 30 by 5 into 2, right? Sorry, sine 30 by 5. So what you will get here is simple thing, that is sine 30 divided by 5 divided by sine 6. So that is giving me a value like 0.966. Sorry, 0.957. 0.957. So, basic thing is very clear to us that if we increase the number of slots in a phase spread, then obviously this distribution factor will be getting reduced. But the idea is that it's very means harsh attenuation it gives towards the higher order harmonics, and that is how we can mitigate the higher order harmonics. And even if we have a non-sinusoidal uh, distribution of space, the space distribution of flux density, we can have almost smooth variation of our time time flux, means no time flux, rather time variation of our induced EMF. Okay. Now just one last one I would like to show you for widespread. Say for widespread, let us take q is equal to 3 or q is equal to 7. Then what we will get for widespread coil? Widespread coil is like, for widespread this will remain constant for, means like here it is always constant for widespread. However, what would happen in the denominator, it is like 7 into sine 60 by 7. So you can figure it out, like it will be it will give you something 0.830. And let me show you another example when Q is very high. So for narrow spread with very high Q, you will have and here it will be, so that will give us that 0.9549, and for widespread it is, for widespread you will get it so it will be like it is 0.8269. So what is interesting things to note here, that like this one, like these widespread coils, uh, they are giving a higher value of distribution factor, and that it indicates that if we like take more higher order harmonics, then this widespread coil will give you more attenuation to the higher order harmonics, right? Now see, I would like to show you for your better understanding that why I am spending so much time on this particular issue, because it is indeed very important that you can visualize what is happening here in that total case. So that is why let me share some picture from the book of Alexander Langsdorff. Oh yeah, where is this? Where it is? Just a minute. So if you see here, you can see that we are considering this field distribution due to some harmonics, like the fundamental is having B1, the magnitude of fundamental harmonic is B1, then third harmonic is B3, fifth harmonic is B5, and for rth harmonic obviously it is B7. Now for any harmonic, what we can write, it's very easy to uh, find it. Like for any space angle, means from here if you start any space angle alpha, alpha can be any arbitrary angle, the value contributed by that harmonic is how much, that is, or you can write that B alpha is like alpha r is equal to BR sine R alpha, right? So from our previous discussion, we know that when the like fundamental will execute one complete cycle, the third harmonic will complete 3 cycles of it. Similarly, fifth harmonic will complete 5 cycles of it. So this here you can understand that when fundamental harmonics will complete one pole, the third harmonic should have 3 fictitious poles. Once again, all these are fictitious because, as I said, that in electrical machine we do not have separately means we cannot have separate existence of harmonics. It is due to some inherent phenomena of means inherent uh, non-linearities that generate this kind of non-sinusoidal nature, and this non-sinusoidal waveform can be visualized as a combination of several harmonics because they satisfy Dirichlet condition, that non-sinusoidal waveform, and we can go for this Fourier analysis and we can have this kind of different but they are doesn't exist physically. Like in case of on the contrary to your musical instruments, you have strings to produce higher order harmonics and you have strings to produce lower order harmonics, but here it is not like that. You are producing already a mixed signal or non-sinusoidal signal unintentionally, or means without any extra effort, and then you are giving effort to figure out which of the harmonics is having uh, or means how this non-sinusoidal waveform can be expressed as a combination of fundamental and other higher order harmonics. So this picture is quite clear that for rth order harmonics, when it is clearly here r is equal to 3, you can see that when fundamental is just one 180 degrees span it is traversing, then third harmonics has already traversed 540 degree, and accordingly third harmonic can be viewed as it is having like your 3 number of fictitious pole, and similarly for rth harmonic we will have 5 number of fictitious poles, so that ER like EMF due to one particular harmonic will be how much, that is root 2 pi if R in phi R. Now this FR is a very funny thing. You can directly write it is root 2 pi. FR is F into R. What is FR? FR is the frequency of your harmonics. So although it is everything is about space angle variation, but still space angle you can find it out. Like if you take a high frequency waveform, then it will within a short time span it will complete more number of cycles. Similarly, in case of your space harmonics, do remember one thing very clearly, that all these harmonics, whatever we are talking about in terms of field, they are space harmonics, but they given generation of time harmonics for our induced EMF, that is the latter part. But for space harmonics, if the frequency is like for fundamental it's F, then space harmonics should be F into R. Even if it is not clear to you, let me show you some other way, like how you write that formula. If you can recall, it was what is your speed in uh, rotation per second, that is so clearly it is like that. Just a minute, sorry. We know that F is equal to, right, this is the formula for synchronous speed. Now if this F is equal to P ns by 2, then for same speed, same amount of rotation, you can see that this will give you the number of pole for fundamental. When fundamental pole is 2, the number of pole for fifth harmonic will be how much? It is 10 times, right? So what we can write here, just a minute. This ns is what? This ns is rotation per second of your machine. This ns is actually your mechanical motion, which remains same for so which remains same for all the cases. However, what you can see that Fr is equal to how, what, instead of 1p you will have Rp. So what we can say, Fr is R into F. So here we can write it is root 2 pi F into R n, that phi R. Now see what will have here for this. So here you can see that what about the flux, that is phi R. Now that phi R will be, we can write it like 2 by pi BR pi d L, that remains same for all the machine. However, it will become for rth harmonics. So if this BR is your field, means flux density for rth harmonics, then one R factor will come, and that is why this phi R will become weaker. Now see what we are having here. This for distributed winding, like if the adjacent slot angle is gamma, then we will have our breadth factor for fundamental, as I told you, or let me write it for rth harmonic. It is sine QR gamma by 2, and here it is Q sine R gamma by 2. So it's quite clear. Now I would like to show you something like a very interesting chart. I have also taken this from the book of S. Langsdorff. So here you can take a screenshot of that, and you can for your own practice you can do it the calculation. This indicate the order of the harmonics, and here it is the q slots per pole per phase. This vertical side is the order of the harmonics, and this side is the number of slots per pole per phase. So sometimes you can see that for certain harmonics we are getting something like we are getting negative sign. So what is the interpretation of that negative sign? Like if you select q is equal to uh, 2, then 7th, 9th, 11th, they will be like 180-degree phase shift, means the induced EMF will be in negative phase with respect to your fundamental, right? So that is why they are means with corresponding to that. If you are not getting, let me do it for you. Like it is for 7th harmonic 2. So just a minute. Now let us consider the effect of induced EMF in a fractional pitch winding. Fractional pitch means the winding in which the coil is not having its full pitch. So how we can do that? Like let me show you by sharing one diagram of fractional pitch winding. So you can see it here that had we considered a full pitch winding, the another side of the coil should be exactly pi angle apart, pi angle electrically apart. But here it is not the case. I have discussed many cases of short pitch winding, like how to realize short pitch winding. But now we are going to see that what is the impact of having a short pitch winding. That is very important. Now, one thing in this picture, it is clear to you, like uh, if we have a short pitch winding like by an angle 36-degree, then what we can see that by a time when our like the fundamental harmonics complete your one half of its complete waveform, then it will complete that 5 complete cycle. So here, if we can by any means, if we by doing so, if we can ensure that if we reduce the coil span in such a manner that within like within our pitch, our coil pitch, the average of your fifth harmonic becoming 0, then it will be like how we can get that fifth harmonic will becoming 0. Like here, if you see this picture, then you will be able to understand, like these are let us count the positive and negative lobe. Here you can see that we are having two complete positive lobe. From this line to this line, we are having complete two positive pole lobe, and here if you add these two, like let me color it. This is one positive, this is one positive. Now this is one negative, means partial negative, this is one complete negative, and this is one another partial negative. So if you add them together, then what you will get? Then you will get the sum over one coil pitch is giving you 0. That is very interesting, and this 0 will only get when rho is equal to 36 degree. However, we would like to mm, get a complete formulation instead of like this kind of kids like drawing. We will like a mature formulation of what we are trying to say. Like you can see that here these two belts of conductor. So effective EMF, if that total is E1, this E1 is what we have already studied, that is E into sine that q gamma by 2 divided by q sine gamma by 2. So we have already studied the effect of distributed winding. Now this E1, this one is for full pitch. Now if we said we want to consider the one side, then without any loss of generality we can say that it is E1 by 2, that is the 1/2. Now the spread of the coil, if it is exactly pi, then we can get some value. The other half will also have an induced EMF E1 by 2. But if it is not the case, it is somewhat less than half, then what would happen? Let us consider the instantaneous EMF across this group. The instantaneous EMF across this group at an angle theta will be how much? This is root 2 E1 by 2 into sine theta. I am considering it only for the fundamental EMF. The fundamental EMF will follow the fundamental flux density waveform in space. So it is this value. Now, what about the right hand side? Right hand side will be how much? Right hand side will be this set of conductors will have theta plus pi x. What is pi x? Like x pi is that x is the fraction by which you have reduced your pole pitch from this coil pitch from pi. Now your coil pitch is not same as your pole pitch. So you are having this like E1 by root 2, the total coil is like sine theta plus sine theta plus x pi, right? And this is for fundamental. For rth, what you will have? So let us do it for in general instantaneous value. It is oh sorry, I made a mistake. Like instead of plus we should write it like it is we connect it in such a way, this should be minus. It is always minus. Why minus? Because for means full pitch, when this x is equal to 1, like your coil pitch is equal to full pitch, then also you will get, this will give you what, this will give you together, uh, this side will give you plus sine theta, so it work. So in this way we should write it like minus, and then here it will be sine r theta minus sine r theta plus x pi for instantaneous value of rth harmonic. You will be getting, it will be root 2, and obviously when you are considering its rh, then it is u1r. So u1r, or better to say er, er is u1r. Just for sake of representation, I am dropping on subscript value. So that will give us sine r x pi by 2 and where this angle is so this is the expression, and this particular factor, this one, like we can see that we can write it is like this fractional pitch EMF. We are getting a factor like this is known as pitch factor. This can further be written as like, we can have it like x pi. So further manipulation will result in what is rho? Rho is this much, like rho plus x pi is equal to pi. So rho is the pitch amount, so again this will give you 1 irrespective of r. So your kp is cos r rho by 2. This is known as pitch factor, and the EMF E at any instance is like your 4.44 kp, or let me write ER, kp fr in phi. This is the generalized expression of EMF. Now, how this generalized expression of EMF will help us to realize more sinusoidal type induced EMF, that we will see in our next video. So, till then, you means analyze all this